Hi, everyone. Welcome to our webinar, and thank you for joining us. We're happy to have you here today. I'm Finn Swan. I'm a water industry specialist here at Esri. Welcome to the third webinar in our Getting Started with ARC Hydro webinar series. This webinar is titled Working with the Wetland Identification Model. I want to remind everybody that this webinar is being recorded. The recording will be posted on the webinar registration page and be available for on-demand viewing. You should receive a follow-up email that includes a link to that page. It can take several days to publish that recording, so you can expect it to be available sometime next week. This webinar includes a few polling questions, so please keep an eye out for those and participate when you can. Throughout the webinar, we will be referencing several resources. We will be sharing links to those resources in the chat dialog box, so keep an eye on the chat box to access those resources. I encourage you all to post your questions in the questions dialog box during the webinar. We will answer as many questions as time allows, and we will also be doing a Q&A doc that we will follow up with you all at the end of the webinar. At the end of the webinar, a survey will launch. This is a short survey and will only take about a minute. Please complete the survey. There's only a few questions, and your feedback is very important to us. Once again, I wanted to introduce myself. My name is Finn Swan. I'm an industry specialist on Esri's water industry team. For those of you that don't know me, I've been at Esri for about 6 months now, so I am relatively new. So if it's your first time seeing me, it's nice to meet you, and I hope to see you in person soon. Before coming to Esri, I was a customer for quite a while. I worked at a water utility as a GIS specialist. But even as an Esri customer, I didn't always know where to find information on Esri websites and how to connect with Esri teams. So I'm going to share a few resources with you that I hope you find useful, and then I will be passing the presentation on. These are the people at Esri that support water resources. I'm not going to introduce everyone individually. Instead, I just wanted to put faces to names. But today we do have Gina and Dan joining us. Our team has attended several conferences this year already. Our last event this year is the AWRA Annual Water Resources Conference in Seattle, and that is November 7th through 9th. If you're attending this or any other events that we may be at in the future, please connect with us, introduce yourself, and let us know about your work in water resources. We love to hear and see what you guys are doing. Esri's website is a great place to find information. These two web pages, Water Resources and ARC Hydro, include information about how Esri technology supports water resources, but they also include stories from our customers, documents like technical papers, and information about events that we plan to be at. In addition to our web pages, the Esri community has a group dedicated to water resources. The community is a great place to ask or answer questions, find blogs, videos, documentation, and more. Another way that you can connect with our team, share your work, and ask questions is by participating in our water resources office hours. This is a full hour dedicated to discussion. We want to know about your work, challenges you might have with the solutions, or just get to know one another. Each office hour will have a topic, but we are pretty flexible in our discussion. You can find more information about office hours on the Esri Water Meetup, which the QR code there, and we should have a link in the chat as well. And you hopefully heard it here first. We are planning to host our annual ARC Hydro meeting at the Esri UC in San Diego. It is the Sunday before the actual week of UC, and that's going to be July 9th, 2023. So keep an eye out for an announcement for that in the Esri Water Meetup, and I hope to see you all there. In addition to our Water Meetup group, we use Twitter and LinkedIn to share announcements and information. If you are on social media, follow us on Twitter, and please connect with me, any of my colleagues on LinkedIn, as well as joining our LinkedIn Water Resources group. Today, our presenter is Gina O'Neill, an ARC Hydro expert and author of the WHIM toolset. Hi, Gina.
Hello, Finn. Thanks for the intro.
Of course. And I'm going to turn my camera off and pass things off to you. So,
sounds good. Let's get started. All right. So welcome, everyone. I'll keep my camera on just to introduce myself and then go incognito for the sake of our internet bandwidth. But welcome. I'm going to be talking to you about an ARC Hydro toolset, the Wetland Identification Model, or WHIM, today. And before we get started, I wanted to kick us off with a poll. So you should see that popping up. Have you used ARC Hydro?
Yep, and I'm going to drop that poll in here right now. So please answer it as you feel comfortable, but you'll see the question is, have you used ArcHydro? And the available answers are yes, often, yes, sometimes, and no, I have never used ArcHydro. And I see a lot of you are answering already, so thank you very much for that. I'll allow a little bit more time for you to get your answers in, but just to keep you in the loop, Gina, since I know you can't see it, we've got about 70% of people saying that they've never used ArcHydro. About
Cool.
28% saying yes sometimes, and only 5% saying yes often. So I'm going to go ahead and close the poll, but the final results are 67% no, I have never used, 28% yes sometimes, and 5% yes often. So
awesome. So we have some newcomers. And Finn, can you still see my screen?
I can, yes.
Okay, awesome. So a follow-up, we may have a similar pattern in this poll, but I'm wondering if any of you have used WHIM already before this webinar.
Yep, and I'm going to drop that poll in right now, so you should see it pop up on your screen relatively soon here. And I see some of you are answering already, and I kind of expect from the answers to the first poll that we're going to have a lot of people who have probably never used WHIM either, but we will see what we get here. I will leave it up for a few more seconds, but we've got already going with what I said, about 96% of people saying that they have never used WHIM. 4% saying that they have tried but do not fully understand, and 1% saying I use it often and I'm comfortable with it. So congrats to that 1% there.
Yeah.
So
I'm gonna that 1%.
I am gonna go ahead and close the poll now, but the final results are 94% no, never used, 5% yes, I have tried but do not fully understand, and 1% yes, I use it often and am fully comfortable.
All right, thank you. Well, great. So we have a lot of newcomers to WHIM and to ArcHydro. I'm glad that we have the next hour to chat about WHIM, and hopefully you guys are excited and start using it and reach out for help. Quick intro to myself. So I've been with Esri for 3 years, and I'm in our Denver office. Before coming to Esri, I was studying hydroinformatics at University of Virginia, which really tied me in nicely with Dan and some of the other ArcHydro team members as part of that academic family. And my research actually resulted in the creation of this workflow that has now become the Wetland Identification Model, WHIM. So I feel it's a project that I really care a lot about, so I'm really excited to share it with you guys today. At Esri, I'm a data scientist / technical consultant, so I do a lot with Python workflows, machine learning, and AI. And I'm also an ArcHydro team member where we continue to develop new hydrology-based tools for you all and maintain and grow that ArcHydro toolset. Okay, let's get started. I will go incognito. So first, a little bit of motivation for this need to automate wetland identification. In the wetland science community, in the conservation and planning community, there is this pressing need to be able to streamline the process of mapping existing wetlands, potentially restorable wetlands. And that really gets to the fact that wetland geospatial data are invaluable for these wetland conservation, permitting, and planning activities. Think about when you go in and do an environmental impact assessment, mitigation banking, it's really important to know the distribution and the location of wetlands in an area. In our traditional methods, which rely on photo interpretation, going into the field and physically confirming wetland characteristics, these are two extremely costly processes, both in terms of money and time. And kind of emerging, I'd say in the last decade, there is this marrying between GIS data and machine learning. And that combination is offering or creating new opportunities to be able to streamline those manual processes related to wetland identification. And while GIS data machine learning can't replace boots on the ground and having a wetland scientist physically being present to confirm wetland characteristics, it can really help to screen large areas for initial wetland distribution, or to provide a starting point for manual wetland class assignment. And further, this need to streamline wetland mapping, it is even more so motivated by the National Wetland Inventory, or NWI. The NWI recognizes that their current and likely future budgets are insufficient to continue producing and maintaining NWI data with the current approaches in place with that photo interpretation and field surveying. And for that reason, they have a long-term goal to be able to create better, faster, cheaper wetland data. And this is an effort that several excellent organizations are a part of, with a lot of different researchers and scientists working towards creating tools that can lead us to that better, faster, cheaper wetland data set. And through our collaborations with NWI, WHIM is identified as having potential to be a strategic component in an updated semi-automated workflow. All right, I have another poll here for you. Do you use GIS data to support your wetland mapping or conservation activities?
Yep, and I'm going to drop that in right now. And this is actually a multiple choice, multiple response. So you can pick all that apply to you. And so the question is, do you use GIS data to support your wetland mapping or conservation activities? And please select any and all that apply. Yes, NWI data, yes, soil data, yes, elevation, or no. It looks like a fair amount of you are choosing your answers already, so thank you for doing that. It's a pretty even spread between elevation, soil, and NWI. I know, so it looks like the most popular one so far is elevation. But then soil data and NWI are pretty close behind it, and almost nobody is saying no. We got about 10% of users saying no, and so I'm going to go ahead and close the poll. It looks like about 75–80% of you have voted here, and Gina, I will give you the exact answers in a second here. So we've got 79% of people saying yes, elevation data. 65% saying yes, soil data, 58% saying yes, NWI data, and 8% of people saying no.
Great. All right. Thank you, Finn.
Yeah.
Okay, so I'll take that as it's no surprise to this audience that those ancillary GIS layers can be extremely helpful in estimating where wetlands are likely to be. Elevation data is really key since it is very high resolution and it's freely available. And as we'll talk about in a minute, that's where WHIM tries to really get the most bang for your buck by seeing how far can we go with just elevation data. Then as far as using NWI and soil data, I'm sure you all have kind of struggled with having some out-of-date maps or soil data from Surgo that is a little bit too coarse to find the smaller wetland features that you're interested in. So with that, we're going to dive into WHIM, just kind of go over its functionality and see how WHIM attempts to get past some of those resolution issues or, say, date issues of other popular ancillary GIS layers. All right, so an overview of WHIM's functionality. WHIM aims to infer wetland likelihood mainly from geomorphology. That is because in its baseline implementation, it works with high-resolution DEMs. However, it's designed to be very configurable, very flexible, such that users could include other wetland indicators, maybe do have access to higher res imagery or higher res land cover data. You are able to include that along with the baseline WHIM inputs and really configure it to be best fit for your use case. And aside from its functionality, WHIM aims to provide value for conservation, permitting, and policy. The outputs that WHIM provides can be used as a preliminary screening for wetland locations. So again, if you have a very large area of interest, where can we give our or get our educated guess for, what are the high priority areas, where are wetlands most likely to be in that large area? The outputs of WHIM also serve as a way to distill many ancillary layers into a single actionable data set. We do have a lot of data sets out there that are hosted by our federal and state organizations, and sometimes clicking through them and looking at their overlaps manually can also be time consuming. So WHIM is a way to automate that process and distill it down. And finally, the outputs of WHIM hopefully can guide and streamline field surveys by helping you decide where to begin, where's high priority areas, and it can also serve as a starting point for other geospatial analyses, such as going in and delineating wetlands manually or starting to classify them. As a tool set in ArcHydro, WHIM is available for ArcGIS Pro, and you'll see that there are quite a few tool sets associated with the Wetland Identification Toolbox. We do have a user guide that will be sent out in a later email that goes through how you string these tools together, what is the anticipated workflow, and how you can go and maybe run some of them multiple times as part of your model development phase. You may also notice if you have installed ArcHydro recently, your toolbox may not look like this yet, but these updates are coming, so please keep an eye out on Esri Community for that. So all of these tools are used to execute this very high-level representation of the WHIM workflow. WHIM relies heavily on two main inputs. There is a high-resolution digital elevation model, or DEM, and then some sample wetlands. So starting first with the DEM, WHIM automates a derivation of 3 different hydrologic wetland indicators, and these provide a proxy for near-surface soil moisture. So trying to get a higher resolution representation of saturated areas that maybe can improve on what you can get from just Surgo data. So those wetland indicators are then fed into a machine learning model along with some examples of wetlands. We'll talk more and kind of unpack this part later on. And then once you have a trained model that knows how to relate your wetland indicators to the example wetlands you have fed it, you can then run a model inference or apply that model and generate some wetland predictions. So, and then in addition to just that baseline workflow, the configurability of WHIM comes in with, number one, this being automated and something that you can run many iterations of and kind of hone your model. You have the option to include, along with these hydrologic wetland indicators, some imagery, soils, vegetation. Really, if it is a raster and it has the same resolution as your hydrologic wetland indicators, you can add it in to help improve your model. And then after you have your wetland predictions, we have new tools that will post-process those predictions with just some simple geometry functions, and you can also automatically generate an accuracy report. Now from here, I want to dive into some components of this workflow and just try to remove any sense of a black box that's included here. So we're going to talk a little bit about the step 1, deriving the hydrologic wetland indicators, and then we're going to spend some time hopefully demystifying machine learning and the specific algorithm we're using here, which is random trees. All right, so starting off with that step 1, deriving your hydrologic wetland indicators. So before even applying any equation to your DEM and getting some of those derivatives, WHIM implements a smoothing technique that is targeted to work very well for high-resolution DEMs and to work well for DEMs that you want to model hydrology with. And to demonstrate how this smoothing works and the impact that it has, we are going to look at a cross-section across these 2 wetlands. And let's say that for this cross-section, we have a DEM and we're going to derive curvature from it. If we look at that cross-section and see how curvature changes, so this is the distance along this transect or this cross-section, and the red notes where that cross-section is overlapping with a wetland. What we would hope to see is that the curvature is going to look different or significant within those wetlands because then wetlands become easier to detect. However, when you use these high resolution DEMs, you can get a lot of microtopographic noise or just more detail than you really need. And for that reason, WHIM offers 4 different methods for smoothing your DEM before you start to derive any wetland indicators from it. And smoothing is implemented as a way to decrease microtopographic noise while not losing the important detail. And I just want to kind of hone in on this one here, pronomalic, which will be included in the demo later on. You can see that this smoothing method really smooths out the noise that is between geomorphic barriers, but then across those boundaries where we see something interesting happening, it retains that level of detail. All right, now diving into the hydrologic indicators. So these are the baseline wetland predictor variables that WHIM will automate for you. And these are all going to be created from that smooth DEM. As I run through these, just compare the representation of the indicators to what this imagery is showing for the same area. So first, WHIM will create a mean curvature raster, which is a way to summarize the intrinsic concavity or convexity of an area, so separating convergent versus divergent areas. WHIM will also calculate the topographic wetness index, or TWI, which is a fairly common elevation derivative for things like wetland identification or streamline identification. And if we look down at TWI here, we can see the areas that are darker blue are being modeled as wetter. And then as we get to those lighter blue shades, those are relatively drier areas. And we can start to see how that's matching up with the riverbed that we see in other channels coming off of it. Similarly, for curvature, we're seeing those channelized areas represented. If you're not familiar with TWI, it looks at the slope and flow accumulation of all of the areas of your landscape and kind of the ratio between those two things. And given those two factors, it can identify the areas that are low in the landscape, like at the bottom of a valley, and that are also very flat, as areas with a higher potential to be wet because they're going to probably accumulate water and hold it there. So this is a way to see relative saturation in the landscape as well. And the third baseline hydrologic indicator is this depth to water index, or DTW. And we can see here that as we have those kind of more turquoise hues, that is modeling wetter areas in this landscape, versus the upland drier areas as we kind of move up to those brown and white colors. So DTW is looking at a cost distance of the areas in your raster to the nearest surface water. And it's measuring that cost in terms of slope. So that is to say that areas that are very flat and near surface water are likely to be wetter. So this is really doing a good job at capturing those riparian areas, or maybe those depressional areas that are still fairly close to surface water and are likely to see some saturation. And one thing to call out here is that the new versions of these tools feature two new functionalities that are included in our core hydrology software. The first is A-star flow routing, and that is implemented with the continuous flow tool. There's a link to that later on if you haven't worked with that yet. And then any of these, wherever slope or curvature is used to derive these hydrologic indicators, those are being calculated using an adaptive neighborhood method. And you can see just a quick illustration of what that adaptive neighborhood method does. But in summary, rather than deriving slope for a 3x3 window for all of your raster, this new method will instead estimate if you're in an area in your raster with a lot of changing topography. If so, let's capture slope or curvature on a smaller scale so we don't miss any details, versus if we are on a plateau or an area that's pretty flat, let's try to capture slope and curvature at a larger scale. And in that way, we're able to capture hydrologic patterns at more optimized scales. All right, and now before we dive into demystifying machine learning, we have another poll here for you. How familiar are you with machine learning?
All right, let me get that poll in there for you guys. So, like Gina said, the question is, how familiar are you with machine learning? And this is just a multiple choice. Please select one. I use machine learning often and I understand it well. I've used machine learning, but I do not fully understand it. or I have not used machine learning. We've already got some answers coming in, so thank you guys for that. So far, leading the pack is I have not used machine learning. About half of you have answered so far. If I was to answer this, it would be I've used machine learning, but I do not fully understand it, and that was quite a long time ago. It looks like about 75% of you have voted, so I will leave it open for just a few more seconds. All right, I'm going to close it here and give you the results, Gina. So we've got about 56% of people saying they have not used machine learning.
Okay.
36% say I've used machine learning, but I do not fully understand it. And 8% who say I've used machine learning often and understand it well.
All right, great. Well, that is a good split, as I plan to dive a little bit deeper into the basic concepts of this specific machine learning algorithm. But for the 8% of you that do use machine learning pretty often, I'm curious, how do you implement it?
Yeah, and I am going to drop in one more poll for those of you that do use machine learning. How do you implement it? And your options here are with Esri software, with another software, or with Python or R directly. And yeah, my very short experience with machine learning was within Esri software. I was trying to do landscape identification stuff using like red, green, blue, and infrared values from aerial imagery. So that was a fun little project.
A classic.
Yeah, so I see you guys are already voting, so thank you for that. I'll leave it open for a little bit longer, but right now we've got Esri software leading the pack, which is, great news for us. I'm glad to hear that. And just behind it is Python or R. And I'm actually not really aware of other softwares for machine learning, but don't work much in that space, so I'm not sure what they would be. We've got about 30%, 40% people voted, but it doesn't look like much more is coming in, so I'm going to go ahead and close it. And the results from that are, we've got 50% with Esri software, 20% with another software, and about 30% with Python or R directly. So
awesome, thank you. So yeah, great that some of you are already leveraging kind of software with user interface that Esri provides to run machine learning algorithms. My hope with designing WIM the way that I did is that machine learning can be a little bit more approachable, because you don't have to sift through lines of code. You can have a little bit more guidance as you define your inputs and different model parameters. So with that, let's dive into the random trees algorithm. So this is the machine learning engine that WIM uses. A quick note, if you're familiar with the random forest algorithm, it is the same algorithm that I'm talking to here. The name random forest itself is trademarked, but the algorithm, of course, is open source. So the basis of random trees is a single decision tree with some targets. So in our example, we're trying to identify wetland versus non-wetland. And then along with those targets, a decision tree has predictor variables. In the baseline implementation, we can think of these as whether something is convergent or not, whether something is near surface water, and if an area has high flow accumulation. And what the decision tree is going to do is figure out some different splits and decision routes between your predictor variables, and use that to try and decide how can I split my training data into groups that are very different from each other, but where the data within each group is very similar to each other. So what's the most optimized way to group these things given my predictor variables? And a decision tree is going to do that given examples of your targets, which is referred to as training data. So here we can think of this as 4 different examples of wetland and non-wetland. And as the different examples of each target is fed through this decision tree, the model starts to learn how to relate your predictor variables to your target. So from this example, it may learn, okay, wetlands are close to streams and they're convergent, versus its next example, it will start to build up a rule that non-wetlands have low flow accumulation. And then the jump from there to go from a decision tree to random trees or a forest decision trees is that instead of just using a single decision tree, this algorithm uses multiple, and each of those trees are going to see a different subset of your training data, and it's going to decide to use those predictor variables a little bit differently. And by implementing this kind of add-on, the result is that you're going to have a more robust model that sees a lot of variations of your training data and is going to use a majority vote between the different trees before it makes the classification. And this is the reason that random forest is very popular. It really can make smaller training data sets go a lot further because of this kind of bootstrapping that it implements, which in the world of trying to identify wetlands, trying to have enough training wetlands data that you're confident in, this really becomes critical to know how far can I go with limited training data. All right, so hopefully that explains what random trees is doing in the background and why it's important to have good examples of wetlands versus non-wetlands, because you want the model to learn the wrong thing, and what the role that predictor variables plays, or the role that predictor variables play. Again, the features that you give your model to distinguish between your targets is critical, because if you choose something that doesn't allow it to really split wetland and non-wetland groups apart, then you may have a model that's kind of confused. All right, we are now going to dive into a demo, putting all of WHIM together now that we've kind of reviewed some individual components of it. So I'm going to run through a WHIM application for a study area in the Hoh watershed. This is in Washington State. You can see that I'm going to work with just a single HUC-12, and we can get a quick sense of what the topography looks like in this area. We have a bit of a valley along this stream bed and a little bit more on the edges of this watershed. And I want to quickly thank the authors of the WIP tool for sharing this data set with me. And this small HUC-12 that I'm using is part of a much larger study that they're undertaking. So it's been great to collaborate with them and share some ideas. Oh, and one more thing I wanted to add here. The reason that this watershed is included in those authors' study is that the NWI hasn't been updated here since the 80s, I believe. It significantly underestimates the wetlands in the area. And this area has a lot of forested or cryptic wetlands. So when we are looking at forested wetlands, that's where topography can really come in handy, as we don't have to worry about that tree canopy as much looking at a bare earth DEM. All right, the main components of the WHIM workflow, they're really the same as any kind of machine learning model that you're going to put together, or that model development phase. You're going to, number one, calculate your predictor variables, which are the things that the model can use to distinguish between wetland or non-wetland. You're then going to train your model. You're going to apply that model by running model inference, and then you're going to assess your results. So step one with WHIM, predictor variable calculation. Before we derive our curvature TWI DTW, we're going to smooth that high resolution DEM. As a reminder, this specific method from the Malik, what it's going to do is encourage any smoothing that is within geomorphic boundaries as it estimates. And anything that's across the geomorphic boundary, it's going to penalize any smoothing. And this is just going to give you a cleaner representation of the land surface before you start to derive some hydrologic patterns from it. So with our smooth DEM, we can now calculate our curvature raster for our study area, then our TWI raster for the study area, and then our depth to water index for the study area. Quick note here that DTW does require some surface water raster as an input. This can be taken from the NHD, or you could derive your own streams with other ArcHydro tools or spatial analyst tools. Now we move on to model training. this is where we are feeding those decision trees examples of wetlands and non-wetlands, and we wanted to start learning how to build a set of rules to relate our hydrologic indicators to those targets. So ideally, you may have a small subset of this area that you have delineated and you know the full coverage, where wetlands are and their extents. A drop down from there could be having to use NWI data, which is what's mapped here. However, in this area, the NWI is very much out of date. So what the authors of the WHIP tool from University of Washington and TerrainWorks were able to share with me were a set of their own point observations that they looked at NWI, aerial imagery, and field visits to kind of hone in on some point observations that they're very certain in, being wetland versus non-wetland. So what we're using in this demo for training data is actually just a very small but well-verified set of wetland and non-wetland pixels. And to see an example of that, imagine this red pixel here being an example of a true wetland that the model will try to learn some rules from. These two sets of pixels here being verified examples of non-wetlands. So all in all, we have about 100 4x4 wetland pixels to learn from, 150 4x4 meter non-wetland pixels to learn from, which is pretty small to run some predictions for an entire watershed. So now we can advance to training the random trees algorithm. We're going to pass the training raster that pretty much contains these known wetland and non-wetland pixels. And then we're going to list the predictor variables we want to use. We have curvature, DTW, TWI, and the main outputs. One is this trained model file, and this file is going to store those relationships and dependencies between your predictor variables and your training data. And then during this training process, we're also going to create a text file that gives us a measure of relative importance of each predictor variable to train the trees. So this can be a really handy metric as you continue to refine your model. Here's an example of what this output looks like. And we can see the importance of each of these inputs. And they're all pretty neck and neck, but we can see that the DTW input was a little bit more important during the model training phase. Now that we have our trained model, we can use that as an input to run random trees. We're going to pass a composite version of these three predictor variables. And we're going to say, apply your rules that you have learned given these inputs to the rest of my area and generate some wetland predictions. So one output that we get from this tool is what I would call a hard classification. So it's what we're visualizing up here. These are every pixel in your raster has been classified as either wetland or non-wetland. And in this example, we have applied another WHIM tool that does a geometry-based cleanup of wetland predictions so we can visualize them as polygons. So we can see definitely some area of interest along that stream bed. We can see some very, very low priority areas on the edges of our watershed and some other little pockets that maybe don't need a lot of time to manually confirm. And another prediction output that WHIM provides is these probability rasters. So here, instead of a hard classification where everything is assigned as a wetland or non-wetland, we instead have the probability of each raster cell belonging to that wetland class. So here we can see as we move from blue, which is wetland probability of 0, up to yellow and red, that probability of a wetland increases. And this is where a decision maker can really decide what's that trade-off? Do I want to be conservative with my wetland predictions and only look at where it's an 80% probability or higher? Or is it very costly to miss wetlands? And do I want to consider anything that's 40% probability or higher? And moving on to just taking a closer look and doing a pseudo accuracy assessment. The WHIM tool does have a tool in place to generate an accuracy report and provide more of a summary, but that's best used when you have some true wetland polygons or true wetland coverage to compare the model to. So instead, we're just going to consider a couple of reference data sets here. So on the top row, we have our our hard classifications, our wetland predictions in this turquoise overlay. And we're going to compare that a bit to what NWI shows, knowing that NWI is underestimating, maybe isn't going to capture all of the details of a riverbed that our tool would be. And then down here, we're going to look at our wetland probability raster that the tool created and just compare that to some of our verified wetland and upland points that we have. So one example to call out here is we see in purple a verified wetland observation that is overlapping very well with a high wetland probability. If we take a look up at the wetland prediction view of that, we can see that that is giving us confidence that WHIM is properly augmenting the NWI data set, where NWI is just outlining a very thin streamline. WHIM is really saying more of this riparian area is likely to be wet and saturated. Moving over to here, we see another similar observation where NWI has this smaller polygon mapped as a wetland, and WHIM predicts that there is more wetland around it. Two of our verified points are backing up that prediction. And on the flip side of that, of course, all models are wrong, some are useful. We can see here where there is a known upland point, WHIM did do some wetland predictions, so maybe there is some additional training data we can introduce or another predictor variable we can introduce. I think in the interest of time, I will go past this. There's just another snapshot of some some WHIM results, but very quickly we can see some more confirmed augmentations of the NWI data that is matching up with some verified wetland observations. So at this point, we are done with using WHIM, but any model creation is meant to be an iterative process. So let's revisit this four-step process, and remember, you, the user, are the expert for this landscape, and WHIM is meant to be configured to work for your area and for your use case. So that means that the user should determine what is the model missing based on the results that you assessed, and then iterate on your model configuration, add in those things that are missing, continue to hone that model. So we go from assess results and maybe back to predictor variable calculation. This wasn't meant to look like a smiley face, but sure, using WHIM is a happy thing. All right, so in this demo, we also want to include some soil data. We're going to grab hydraulic conductivity from Sergo to get a sense of how well the soil can transmit water. And we're also going to grab NDVI, that's derived from the national scale NAPE imagery dataset. These two inputs may not be best for all study areas, but here we're going to go ahead and apply them. And to do that, WHIM makes it very easy, again, to include additional predictor variables. You just have to ensure that these are rasters and that they are resampled to be the same resolution as your input DEM. And then all we do is add them to this drop-down list. We're going to rerun train random trees. It's going to generate a new train model, a new variable importance measure. And this took about 1 minute to run. So that runtime, it's a pretty quick turnaround, and that can change depending on how high resolution your DEM is, how many predictor variables you use, how big your training raster is. So now we have our updated trained model where the decision trees have learned from those two additional inputs. We have a new set of predictor variables, and we're going to run model inference again. So we can see as we swipe this way, old results, new results. So visually, we're getting a lot more wetland confidence around that riverbed. We're seeing some movement of where the original model thought there may be a wetland, and now this new model is kind of confirming that there that that's probably upland. So a quick way to change your model outputs and start off this iterative process. And if we look at a quick snapshot, this top row is that wetland probability when we include NDVI and hydraulic conductivity. And this on the bottom was our original wetland model with just those 3 inputs. One thing to kind of call out here is, well, number one, we have more more confidence in our wetland predictions up top along that riverbed. And where the model was previously predicting a wetland that overlapped with upland points, we can see that that confidence is decreasing, and maybe the model is able to recognize upland points a little bit better. Okay, and now just a couple of minutes to close us out here and then leave some time for Q&A. I want to revisit now, what are the contributions of WHIM in its current state, and where are we headed for future development? So number one, remember that WHIM outputs offer a way to distill multiple GIS layers into a statistically meaningful representation. We could have toggled on and off those 5 layers, curvature, TWI, DTW, and then the soil and imagery layer, and try to see where they overlap. But WHIM automates that process for us, and it's doing that in a statistically based way. Using just the baseline wetland indicators, those hydrologic indicators, that's really a way to map wetness potential. Those specific indicators and the smoothing that we use, those are rooted in academic research, and they're derived from publicly available data from those high resolution DEMs. So low barrier of entry there, and a good starting point. The predictions can inform subsequent manual processes by streamlining and prioritizing areas. And the outputs do provide the flexibility to decision makers to balance that trade-off between wetland overprediction and wetland omission, specifically by working with that wetland probability output. And finally, WHIM allows the ability to configure models specific to different use cases. By that, I mean you can quickly incorporate additional data sets that maybe your area of interest has. You can do so in an automated framework where you can model changing conditions, you can model different scenarios, but just know that the manual efforts are pretty limited because WHIM will run through this framework for you. And finally, WHIM offers automated accuracy reports. So as you run all of your different model iterations, you can quickly generate some statistics to summarize the results. All right, so the development roadmap for WHIM, we have been very lucky to have opportunities to collaborate with National Wetland Inventory and most recently with State of Minnesota. On the right, you'll just see an animation of, I think I went through model iterations A through X, evaluating some additional geomorphologic indicators in a study with NWI. But we're working with them to see how can we configure WHIM to identify depressional wetlands in the prairie pothole region. How can we easily incorporate some emerging scientific data sets? How can we reconfigure it to identify potentially restorable wetlands instead of existing? There's also an ongoing collaboration with the University of Washington. And with that, we're looking at how we can capture hydrology at varying scales. And most importantly, I think, how can we examine similar and existing methods and help those authors by automating more and maintaining their implementations within ArcHydro and take some of that onus off of them. And really, WHIM continues to improve as far as functionality, become more accessible, and address more pain points. The more that we hear from the users, hear use cases, hear your questions on Esri community, and refine the tools around those user needs. All right, quick acknowledgements here. So wonderful collaborators from NWI, the authors of the WHIP tool that provided really valuable data for this demo, Megan and Dan's team from University of Washington and TerrainWorks, and then some additional support from State of Delaware and State of Minnesota. I will leave this slide up for closing. I believe Finn will be sending out these additional resources how you can get started with WHIM. But please do keep an eye on Esri community because there's a lot more to come. Updated WHIM tools for ARC Pro 3, an updated user guide, WHIM Learn lessons, and WHIM training to come. You could always just contact me if you need any of those things sooner. And that is it.
Yeah, and I'm just going to jump in here so we can get started with Q&A, but I will say when it comes to the additional resources, we will be doing a blog post that will have all of these resources available, as well as a Q&A document, because you guys are just asking a lot of questions, which I love, but we're not going to be able to get to all of them here in 9 minutes. But I have tried my best to kind of generalize and group stuff together here so we could get started on them. And then if your question does not get answered, please keep an eye out for that blog post, which should be referenced in a follow-up email with these resources and that Q&A document with those questions answered. So the first question I'm going to throw your way, Gina, is how could you modify WHIM to identify potentially restorable wetlands? Yeah,
great question. So keep in mind that you can include things like land cover data to WHIM. So WHIM in its baseline indicators, it's going to model a potential for water to accumulate in the landscape. We can combine that with agricultural land cover data. And so then we can get that significant overlap of where water may be naturally accumulating, but it's in an agricultural landscape and therefore could have been a drained wetland. So just one idea for additional data sets you could include.
Okay. So this was one of the more popular topics and a lot of questions surrounding it. So let's try to go into detail on it. What is the recommended resolution for an input DEM? There's a lot of questions surrounding what a high accuracy DEM really is, what the cell size should be, what's the least acceptable resolution, and also do all of the rasters need to be the same resolution? A lot of questions surrounding that topic.
Okay. Yeah. So when I'm saying high resolution DEM, I'm really thinking of updated DEMs derived from LiDAR, as those have been shown to be more accurate than the older radar-based DEMs. So anything higher than 1 meter, higher resolution than 1 meter, I would sample up to 1 meter. And then this data set, or sorry, this demo is created with 4 meter resolution DEM. And I'd say 4 or 5 is about as coarse as I would go. That being said, any elevation data is better than no elevation data. So don't count WHIM out if all you have is maybe some coarser SAR DEMs, but ideally 1 to 5 meter. And sorry, one other point you mentioned. Yes, all of the predictor variables need to be the same cell size before they're fed into WHIM.
Awesome. Yeah, I was just about to follow up with that. I know I asked you a lot packed into one there. So another one I got a couple of questions about is what is the difference between curvature and profile, and really what is the kind of definition of curvature?
Yes, that's a great question. So there is plan and profile curvature, both of which you can derive in Esri core software. What WHIM is using is a mean curvature, which is kind of taking the average of the different curvature components. And it's really just getting at the extremes of separation between an intrinsic tendency to, be a bowl and accumulate water versus be kind of a mound that's going to drain water. So you could derive both plan and profile curvature and add them in if you want to try that, though.
Okay. This is one that I liked a lot. Is the model designed for only one identification process, or is it possible to use it to identify temporal changes on wetlands? So if you were to, I thought that was an interesting one.
That's a good question.
Yeah.
If you wanted to look at maybe a change in wetland cover or wetland landscape, I would say, you need source elevation data that represents a change in that landscape, so maybe pre and post development. And then you could derive wetland predictions using each kind of timestamp DEM, and then do a more traditional overlay, see what areas have changed. But random trees inherently is more of like a timestamp algorithm versus seeing a time series.
Okay. This one was good as well. What size area is this model best applied to? There's someone saying that they have a DEM layer across like all of Washington? Would it be reasonable to apply it there, or is that too large? Or
Yes, so you do run into size issues because on the back end, WHIM is turning your raster into a NumPy array. So whatever size is the max NumPy array, we have the same limit here. I would say for training data, here I use very little training data, but ideally you have maybe a square kilometer of known wetland and non-wetland area to train on, and then you could apply the model to up to a HUC 12. If you have really high res data, you may need to delineate like a HUC 14, HUC 16, but I would not go larger than HUC 12 at a time.
So let me jump in here, and Gina, I'll give you a breather so you can go and look at some of the questions and pick your favorite one you want to answer, because I think we are getting to a couple of minutes left. So while you are having fun reading the questions, and I tried to answer as many as I could, and I didn't listen to you at all because I was trying to answer questions. But anyways.
Oh, thank you, Jennifer.
I want to answer on a general level. There were a lot of questions about whether this works in ArcMap or in Pro. Archival tools work in both, but some tools will work in Pro, some tools will not, and WIM works only in Pro. So I provided some resources on where to go and download stuff. I urge you all to frequently visit our Hydro Water Resources community page, because that's where we are going to announce all the new stuff. All the documentation is there. There was a question about training. There is training for Hydro that at this point does not include in-person training, like a 3-day Hydro training that at this point does not include WIM. Gina and I are talking about putting together a class that will be focusing on WIM and machine learning in general. So keep looking in water resources. So keep looking for that. And, I'll stop here. Gina, you've got 2 minutes for your favorite question.
I know you answered all of them how I would, though. I think I'll go back to a question about whether training data should be ground truthed. Just remember that your model is going to be as good as the training data you give it. If you supply example wetlands and non-wetlands that aren't actually wetland or non-wetland, the model is going to learn a rule that's incorrect. So as confident as you can be in that training data, whether it's through detailed manual photo interpretation or field visits, the better that your model is going to be. Similarly, the more training data, the more use cases your model can learn from. So as good as you can get it, I would say, is the answer there.
Okay. I think we might have time for one more question, if we can squeeze it in as fast as we can here. I like this one. Are the outputs raster only, or does the tool create vectors in shapefiles, basically?
So in the version of WIM that's available right now, they are both raster based. You get a hard classification where every raster is assigned a 1 or a 0 to represent a wetland classification, and then you get that probability raster where it's assigned 0 to 1, the probability of something being a wetland. We have a new tool that post-processes that hard classification and actually converts all of those wetland cells to polygons, does a little bit of cleaning up of them. So there is newly a way to represent them as polygons too.
Nice. All right. I think that's all the time we have for questions. Thank you, Gina. I know I've fired a lot of them at you there, so thanks for answering all of those. I just want to remind everyone that the webinar was recorded, and it will be made available on that same page that you used to register for the webinar. It should be there in about a week. And just like I said in the beginning, we'll have a post-webinar survey, so please take time to fill that out. It's only a couple of questions. And thank you all for joining us today, and we'll see you next time. Goodbye.
All right. Bye, everyone. Thank you.
Thanks.